Welcome to an example in which we're trying to determine if there is a linear relationship between driver age and number of deaths per 100,000. Well, it says you wish to determine if there is a linear correlation between the age of a driver and the number of driver deaths. The following table, blah, blah, blah. So in other words, what they're saying is, you know, as drivers get older, like 80 years old, do they cause more deaths on the road? Number of deaths? Driver deaths. Do they die more often when they're they getting too old, or maybe really young people? There's not really any super young people, but maybe like 16-year-olds driving. Do they die behind the wheel more often than like 33-year-olds and 40-year-olds? Does age go with more deaths? So maybe as you get older, do you cause more deaths? That's what we're wondering. Is there a linear connection? This is something that happens a lot in real life, in the information age, 21st century. People are often wanting to know, is there a linear connection between two things? In this case, driver age and number of deaths. How do you examine that? How do you research that? Well, let's go to our notes. Let me show you right here. So here is the exam 4 notes. That's what you should look at. Exam 4 notes. Come on down to number 6, testing linear correlation. That's what we're trying to figure out. Is there a linear correlation? Let's go back. I got it actually down here for you already. And you see the name right here, right? Linear correlation. So on the test, you'd see linear correlation and go, oh yeah, I got to go to number 6 on the notes, testing linear correlation. What's the first thing? Put the data in L1 and L2. So you got to go back up and you've got to put this data in L1 and L2. So step 1, put the data in L1 and L2. And you know how to do that quite easily by now. Clear out whatever else was in there before and put the data in L1 and L2. I guess I could write out real quick. You hit Stat. You're already on the Edit menu. You hit Enter. And then you go to the top of L1. You hit Clear and Enter. And then the same thing for L2. And then put in the data. I think you've got it from there. Step number 2. Then you're going to go to Stat and go over to Tests and go down. See what I'm doing right here. If it's following the notes, it says go to the linear regression t-test. So let's go there. We're going to go down to, what number is it? It looks like it's F, at least on my calculator. Might be the same on yours, depending if you have a TI 83 or 84. I think it might be the same, I don't know. Linear regression t-test and hit enter. That's where we need to go. And so when you do that, you'll get some a list of stuff. It'll say X list, Y list, frequency. Then it'll have this funny looking B, which is actually a Greek beta. And then like a funny looking P. And it'll say not equal, less or greater. Or not equal to 0, I should say. Not equal to 0, less than 0, greater than 0. And then that's it. So what are we going to put in for this stuff? Well, our X list is L1, this is L2. If you don't have L1, L2 there, you probably already do. You can just hit second and 1, second and 2. It's probably already there for you. What we're saying is that means L1 and L2 are where our X values and our Y values. And frequency, we always have that be 1. Now, and we're going to choose whatever we have here, not equals. So this will be not equals 0. So, and then hit enter. Okay. So now, and don't be confused by this this P here. In fact, let me just, well, I'll do it right there. That P is actually a Greek R called rho. And why I'm bothering to tell you about that is because I want you to know it's the same as this R. This R is the sample value. And this one is the Greek value, meaning we always use Greek letters because we're saying it's from the whole population, meaning the whole world. And whereas the regular R, the English R, is from the sample of 9 drivers. English R. So whenever we use English letters, so the English R is from the sample of 9 drivers. So have you caught that throughout statistics? We're always using English letters, like R, to represent our sample. And R, what is R? It's the linear correlation coefficient. Remember, we could look at a graph. We didn't graph this one. It would have been useful, though, to look at a graph, but let's skip that. If we graphed these on a graph, meaning like over 30, like these are x values, right? X values, y values, over 35 up 20. So we went over 35 up 20, dot. Over 72 up 25, way over here. Whoops, I lost my graph. Over 72 up, etc. What you'd get is a bunch of different dots, and the question is, would they line up like kind of a straight line? Or would the dots just be like random everywhere, not making a line at all? What would it be? Well, we could look at a graph, but we have a calculation which tells us that, called the linear correlation coefficient. Remember that R is the linear correlation coefficient, and that when R always goes between -1 and +1 with 0 in the middle. R, now I'll say or P, which is really a Greek R, rho. They're both R, basically. And remember, when it's really close to -1, this is line going down, and this is a line going up. And then anything in the around the 0 area is no line relationship. No line relationship. Whereas line down or line up, strong evidence. Either one of these cases on the ends are strong evidence. Remember, if R is close to -1 or +1, if it's down here, up there, there's strong evidence that we have a linear relationship between driver age and number of deaths. If it's close to -1, it's dots going down. There's a line going down. They have a strong negative relationship. If it's close to +1, the dots form a strong positive relationship. If it's around 0, the dots are just random everywhere, no linear relationship at all. So R, or the Greek version, rho, which is a Greek R, even though it looks like a P, tells us that. Now, what's the difference between R and P, or rho, really? Well, the R is just from our sample. So just for these 9 drivers, how much do their dots seem to go in a line? And we're going to use our sample information to figure out something about the whole world. Because that's really what we want to know, right? Whenever we're doing something in statistics, we want to know what's true for the whole world. We don't just want to know, hey, these 9 drivers, we really care about these 9 drivers. How much do they fit a line? No. We want to know for the whole world, for the whole population, the whole world. Do drivers that are older tend to have more deaths? That's what we want to know. Should we take away people's licenses after 80 years old? That's what we're wondering. That's what we're really wondering. So what we're really going after is the Greek R, the rho, that looks like a P. We want to know about and we're using about the whole world. Is there a connection between driver age and death for the whole world? And to figure that out, we're using the sample values, right? What we get from these 9 drivers to figure out what might be true for the whole world. Okay. So, if you put all this information into your calculator, you L1, L2, frequency 1, calculate, and you go on down, you'll get an R value. Here's what I got. I got an R value of 0.2174. 2174. I have to round to 4 places, and which is not a very good. That's an R value around 0. It looks like there's no linear relationship. My p-value, where's my p-value? There's my p-value, came out 0.5742. Remember what p-value is? The probability that this that this data is just luck. So if these dots did form a line a little bit, they didn't do it much. That's terrible. They're probably pretty random. What's the chance that any resemblance to a line is just luck? Pretty good chance. 57% chance of luck. How does that compare to the alpha level? Here's our alpha significance level, 0.01. That's alpha. 0.01. Well, we're certainly way greater than that. Our p-value is way greater. So what we're saying is we want to see if these 9 drivers' dots seem to form a line or not. And if they do, maybe they just appear to form a line, and maybe they're just a lucky 9 drivers, but their lining up is just luck, and really it's not true for the whole world, the whole population. What's the chance that any resemblance to a line of these 9 drivers was just luck? There's a really good chance, 57% chance, because the dots didn't even line up hardly at all, it turns out. So that means it's just luck. There's a very good chance it's just luck. There's no real linear relationship here for the whole world. So what do we do in our conclusion? You probably remember how these conclusions go. Remember the saying we always use? If the P is low, then the HO must go away, right? If the P is low, the null must go. So is our P low? Is our P low? No, our P is greater. Our P is not low, so the null must not. You throw in a couple knots if it's not low. Right? Our p-value is greater. Our p-value is not low, so the null must not go away. So the null does not go away. What does that mean? We fail to reject the null. So the p-value is greater than the alpha. We do not reject the null. We fail to reject the null. Now you might say, okay, Mr. Aaron, but shouldn't we, isn't that the same thing just as accepting the null? No, not quite, not quite. We don't accept it. You know what it's like? It's like a court of law. Remember how a court of law works? Let me go up. So remember the HO is always weak evidence. Weak evidence. And it's why is it weak evidence? Well, it's because it's our assumption. So whereas the HA requires strong evidence. This is like the analogy I always make. It's like a court of law. What happens when you go into a court of law? Somebody's accused of a crime. In a criminal court, somebody's accused of a crime, and you assume what? Innocent. Unless strong evidence beyond a reasonable doubt convinces you that they're guilty. So in other words, I've been on a criminal case where we let a person go. They were being tried for rape, and me and the other 11 jury members, the evidence was weak. Sadly, everybody was drunk, and nobody remembered anything. And so evidence was just not strong. There was just a bunch of unclearness. We weren't going to put this guy away for years and years of his life on weak evidence. Now, did I walk out of that? So we let him go. Did I walk out of that court thinking, I am sure he didn't do it? No, he might have. He might have. But why did I conclude? Why did I let him go? Well, because evidence wasn't strong. It was weak. We started with the assumption that he was innocent, and evidence was just too weak to conclude that he was guilty. That's why I'm not accepting. Like somebody said, do you accept the fact that he's innocent? No, I don't accept it. I'm not sure he's innocent, but I couldn't reject innocence. So innocence was the assumption, and evidence just wasn't strong enough to reject it. So in this case, we are saying weak evidence, because that's our assumption. So you come down here, weak evidence. Well, it's not significant. It's insufficient evidence to make a conclusion about the linear correlation between driver age and number of deaths. Yeah, there's just not enough evidence. We don't have any strong evidence that there's a linear connection. We're not sure there's not, but we're not sure there is. There's just not strong evidence one way or the other.